Section 8.6 is going to continue with some of the ideas with similar triangles, but we're going to throw in some other kind of unique things about proportions. Not everything is going to be involved with strictly similar triangles. Okay, so just remember that. We do have several theorems to learn. And when we're learning, making sure, think about when we talk about these theorems, make sure you kind of look at that picture. That picture is going to kind of be kind of the focal point on a lot of these problems, okay? So this first one is called the triangle proportionality theorem. All right?
Okay.
So obviously
I hear the word proportion in there.
Obviously it's dealing with triangles. Obviously it's dealing with something with proportions, which has been kind of the common trend the last couple sections. So let's read it. It says, if a line is parallel or is a line parallel to one of the sides of a triangle intersects the other two sides. So we have basically a line that's parallel to one of the sides in a triangle, okay?
Right.
Now, segment is part of a line. In this picture, we're talking about segment TU being parallel to segment RS.
Right, but there is a line that continues on through TU. Yeah.
So these two segments are parallel. So that's what they're giving you, all right? Then it says it. What do you think it is talking about?
Probably that line that was parallel to the side.
So this in this case is TU. Divides the two sides proportionally. All right? So let's think about what that essentially means.
Okay, so if it's dividing the sides, and it's obviously not talking about the side that it was parallel to because that side's not being divided. So I'm guessing that it's dividing QR and QS proportionally.
So they're talking about these sides being divided proportionally. So basically, notice that TU, that segment, intersects both of those sides at points T and U. So it's dividing those, basically, that whole side into two segments that are proportional, basically, to the other sides.
Okay.
So what kind of proportion do you think I can write?
So I could say that, like, QT is corresponding, or is being divided, I should say, as proportional with the TR, and the QU is what's being divided with the US. So I'm looking at those pieces that are being divided.
And those two sides, basically, or those two segments, I should say, not sides, those segments make up the whole sides of that larger triangle they're talking about.
Okay.
All right. Now, here's the deal. We know, based on some other properties of proportions, that you could kind of, in a sense, do reciprocal
Rewrite
of all
those,
these.
yeah.
You could say QT to QU is equal to TR to US. So this proportion can be written multiple ways. So just kind of keep that in mind. All right. This is just one way of interpreting that. Now, something more of a little side note. This kind of comes from this theorem here, but another side note is in this particular picture, I'm hoping you see two triangles as well.
Yeah.
And what do you notice about the two triangles?
Those are two similar triangles.
And why are they going to be similar?
Because of angle similarity. With the parallels, I know I have corresponding angles that are going to be congruent.
So these angles will be congruent. These angles will be congruent.
And I don't even need it, but Q is congruent to itself.
So we know that these two triangles are similar, which then means we have some other proportions we can write. Right? So from this triangle proportionality theorem, we could also use similar triangles as well.
Right.
Okay?
This is just, I want you guys to realize that what we're showing here, we talked yesterday about the whole idea of, you know, we can't split up and just talk about a part of a side when we're talking about similar triangles. This looks like the parts, but this is not based off of, this theorem is not based off of the similar triangle idea. It's based off of the triangle proportionality theorem.
So this particular idea doesn't actually use similar triangles, but we can use them to set up some other proportions is what I'm basically hearing you say.
Exactly.
So in other words, if you're talking about comparing, like for example, TU and RS, those are actually sides of the triangles.
And notice that is not part of the triangle proportionality theorem in terms of the pieces. So if I want to talk about TU and RS, I need to be talking about maybe like QT and QR, not just the piece of TR.
So I think to me that's one of the biggest mistakes as well. We keep saying that because it's easy to make a mistake. So when would you use similar triangles? Well, when you're using the sides of the triangle, especially when you're comparing the parallel segments. bottom line, the parallel segments are not the parts that are being divided.
Right.
Okay? So just kind of keep that in mind. All right?
Mm-hmm. Okay, now there's a converse to the triangle proportionality theorem as well. And it says that if a line divides two sides of a triangle proportionally, so what would be the proportion that I could write? What are the sides that are being divided proportionally?
Okay, well, it's because it's the converse of the last one.
Uh-huh.
So it would be, so if I knew AE to ED was equal to AB to BC. So if I knew that, then we can say
Then
that
we can say, when they say it,
that's EB.
EB.
So they're saying that segment EB is parallel to that third side, which is the side that it doesn't intersect, which is DC. So it's, again, we've learned converse theorems before. It's just the exact flip-flop of what we just talked about.
Yeah. So if you have the sides are divided proportionally, then we can talk about the lines being parallel, which could then help us to talk about other pieces of triangles being with some similar triangles depending on what you're looking at.
Which means then other proportions are going to be true. So again, there's all these different things you can say from that. All right, let's apply some of these theorems to some examples.
Okay.
It says find yx.
All right, now I'm looking at this and I do see a set of parallel lines kind of within a triangle.
I love that you pointed that out first.
And I think that's the thing that we need to look for with using these theorems. Because when I see that set of parallel lines, I know that I can use this triangle proportionality theorem. Because I know that that segment VX is actually on a line that's parallel to that side of UY.
So I'm going to make a little note what Ms. Hogarby said. So we know we can use this triangle proportionality theorem because of the fact that there are these parallel given, okay?
Right.
Okay.
And the triangle proportionality theorem talks about the parts of the segment. So like I'm looking at UW, and I notice they give me the whole thing is 18. Well, the triangle proportionality theorem deals with the parts. So I already have that UV is 3. I'm going to mark on our triangle, or I'm going to have you mark, Mrs. Claro, that VW is going to be 15.
And guys, that's the thing. You may not use it, but it's good. You can find it. You never know. It might be helpful. So just keep that in mind. Okay.
Now, I know that it's dividing the sides proportionally. So I'm going to go ahead and write the proportion to say that I'm going to go with 3 over 15. I'll change it up a little.
Okay, and 3 represents that UV. I'm going to make a little note. You don't have to do this.
Yeah.
To
the VW.
And that ratio should equal
the 3 over the 15.
No, with the other
piece. Sorry. Oh, the YX over XW.
So this is kind of based on the proportionality theorem. That's even before we know all the measurements.
Exactly.
And notice YX is this piece right here that we don't know. So that's kind of, this is going to be a helpful proportion as long as we know the other things. So UV is 3. VW we found just now is 15. YX, I'm just going to leave it YX. And again, you can name it just X for a variable, but just make sure we're careful. Is that really what you're finding? Over 16. Okay.
All right. So 15 YX is going to equal 48. And when we divide, we find that YX is 3.2.
Now, this is something that you could easily check, all right? You could see basically, check your proportion. If you put this into 3.2, does 3.2 times 15 actually equal 48? Kind of cross multiply. The other thing you kind of eyeball. Notice here that 3.2 compared to this 3 is a little bit bigger, and 16 is a little bit bigger than 15. So it kind of, in a sense, is logical. If I got YX to be less than 3, that would be an issue.
Right.
All right. So keep that in mind. Now, this is not the only way you could set it up, but this is probably the most useful.
This is based off of at least the theorem we just learned.
This is definitely a great way of doing it.
Okay. All right. Now, for this next one, the question is, are segments PQ and TR parallel? So now we're kind of trying to think about what?
The converse, essentially.
Yeah.
So the triangle proportionality theorem converse. And when you're doing the converse, you have to first know that those sides are divided proportionally.
Uh-huh.
So in other words, I'm looking at the triangle and I'm thinking like PT to TS. Is that equal to QR to RS. If it is, then we can say those are parallel.
Exactly.
Okay.
So I'm just going to mark on my picture so we
All right.
see it. So
that's
we've got
24.
our 24. We have,
SR is 26.
And then SQ, the whole thing was 35.75, which would leave us with
9.75.
Wonderful. Okay, so let's go ahead and substitute those pieces into the proportion that you just set up.
Okay.
So we're going to write
9 over 24. And does that equal 9.75 over 26?
Okay.
So you could do one of two things. You could like simplify each of those, right?
Right.
Or if this is really true, wouldn't cross product have to work?
Right.
So you could multiply the 9 times the 26.
Okay.
And that is, that is 234. And then when I do 24 times 9.75, that is 234 as well. And so those are equal.
So therefore, we know that the sides are proportional. Therefore, we can say that yes.
And the reason why would be what that theorem that you wrote up here.
Triangle proportionality theorem converse. Exactly. All right.
All right. Another theorem, we said we had several. I think we have a total of 4. This theorem doesn't have a name. Okay. That doesn't necessarily mean it's going to be hard to understand or remember. It just probably means we're not going to use it in proofs, which we haven't done a lot of proofs. Okay?
No, we have not.
So this theorem, it says, notice even the picture. It says if 3 or more parallel lines intersect 2 transversals. In this picture, I have 1, 2, 3 parallel lines intersecting the 2 transversals, which are the M and the N. Okay? So that's what you're starting with. Then they... What's the they?
The parallel lines.
The parallel lines. Man, sorry guys, it's freezing on me. Divide the transversals proportionally.
Okay, well this kind of sounds like the triangle proportionality theorem. It's just that it's not a triangle.
And if you think about it, if you extend these out,
they eventually
kind of
would
get a visual of
it,
this, it's going to end up being a triangle. It's just going to have more than 2 parallel lines. This one has 3. So it's very similar to that. I like that you
we
pointed
could
this out.
apply this to a triangle if they had multiple lines even within a triangle. This would still work too.
Exactly. Okay, so in this picture, if I give you R, S, and T are all parallel, okay, then what can we say?
So we could say that UW over WY is equal to VX over XZ. So those would be all the sides that are divided proportionally.
So again, another key here, that proportional idea. We're setting up proportions and finding missing segments, lengths, things like that. All right? I think this one is pretty self-explanatory
especially since we just saw the triangle proportionality theorem.
One more.
All right. So this next
Theorem.
one says, yes, one more theorem. Says that, and again, notice it doesn't have a name. We're just not going to see it a lot in proof, but we are going to apply this quite a bit. It says, if a ray bisects an angle of a triangle. So notice here I've got my angle bisector. I've marked that it's forming 2 congruent angles.
Okay.
Okay. Then it divides the opposite side. So the side that's opposite the angle. So in this case, I'm talking about AB.
Okay.
Into two segments whose lengths are proportional to the lengths of the other 2 sides.
Very wordy.
Very wordy. All right. So let's break it down. Okay. We have that it's dividing the opposite side. How is it dividing the opposite side?
It makes you end up with AD and DB, those 2 segments.
It's dividing that side. So let's make a proportion out of that.
Okay. Well, first of all, think about, this is where you want to think about if what you have to be given. You have to be given an angle bisector, right?
Yes.
First, okay? So I want to stress that because I think sometimes we assume when we see this, we forget about that.
Right.
Okay, so if we don't have an angle bisector, then we can't use this.
Exactly.
All right, so AD to DB.
So this is the side, the opposite side is being divided, all right? And it's being divided to be proportional with the lengths of the other 2 sides. And one thing I want to stress is I have the other 2 sides of the triangle, AC and CB. to know which one to put to keep, to make it proportional, it does matter which one goes on top and bottom. When I'm looking at segment AD, notice AD is adjacent to or connected to the AC. That's the piece that it has to correspond with. Okay? So the order that you see them is actually very important.
Yeah.
All right, so when I'm dividing my side proportionally, I want to make sure that the side that, basically they share that common vertice. Okay, so if I've got AD, then CA is what's going to go on top, or AC, either way you want to say it. And then what corresponds with my DB is going to be the BC.
Now, again, guys, all of these proportions can be written differently.
Right.
Right? I've seen people say, well, AD to AC, and then DB to CB. Those ratios are equal. Notice it's the same. It means the same thing as the other one.
Yes.
Okay.
And even if you did this ratio, look at it. It says the opposite side with its adjacent segment and this opposite side with its adjacent segment. So again, you just have to keep in mind that there's pieces that are proportional, and we have to keep those corresponding pieces in the same location.
Now, this one, again, like all of the theorems today, these are not directly related to similar triangles.
In fact, looking at these don't appear to be similar at all.
So that's why the title of this was saying proportions and similar triangles. There were some things that we could have, but this one actually doesn't. So just keep that in mind. There's some unique things about some of these triangles, but they're not necessarily always similar. All right. Now, this particular problem says, let's find the length of segment DE. So this is our question mark. I'm going to go ahead and make a note of that. We need to find that given this information. So let me start labeling.
Okay. And I notice on there that they've marked that angle 1 and angle 2 and angle 3 are all congruent. And one thing that I hope that you guys are all thinking back is that when we have all of those congruent angles there marked with the transversal, those are all corresponding angles. And when corresponding angles are congruent, I can say corresponding angles postulate converse tells us that those lines are parallel.
Yep. So essentially, this is what we need. Okay. And otherwise, if I didn't know these are parallel, we wouldn't do anything. So really, the thing is why did they give this? They gave you this because now we have some parallel lines. All right. Which now means we can use maybe one of our theorems involving the fact that we have some parallel lines cutting, basically, or intersecting two transversals. Okay.
Right. Okay, so we know that it's dividing these pieces proportionally. So the parallel lines are dividing those pieces proportionally. So I know, like, for example, AB over BC, so it's dividing that into those two pieces, would equal the DE over EF. And since I'm finding DE, that's my question mark, I can easily put in the other pieces to be able to solve the proportion.
And the nice thing is they give you the other three pieces.
Exactly.
All right, so we do
6 over 9 equals DE over 8.
Now, again, reminder, this can be written other ways, all right? Just, just one way of writing it. So you get 9 DE equals
48.
Does that look like a D?
We know it's a D.
I know.
And
DE equals
and when you've got
5 1/3, I think.
Yeah.
Or 16/3.
However you want to write that.
Now, something I thought about as I was cross multiplying, you could always simplify this and actually get the kind of a simplified version. It's not it's kind of a scale factor. It's not really involving similar triangles.
Right.
But you could say this is 2 to 3 is equal to DE to 8. And notice when you cross multiply, when you go ahead and do that and then divide,
it's going to be already simplified.
It's already simplified. So if you want to simplify first before you cross multiply, it might be easier numbers to work with. Yeah. I often, a lot of times, do that. So just an option there for you. All right.
All right, last one. It says we're going to find MN. Now, I want you to just look at the picture and tell me, what do you notice, Mrs. Blairmont?
I see a triangle with an angle bisector, which is the KM. So I know there's a theorem that says that that angle bisector, so that KM, is dividing that opposite side basically proportionally with the other two sides of the triangle. So LM to MN is going to equal LK to KN. Now, I'm noticing some stuff in the picture, or to the right. Let's label it.
Okay. They tell us all of LN is 15.
Okay.
And then they tell us that LK is 3 and KN is 17. Now, this one looks a little bit different because they don't give us either one of these pieces.
And in the proportion, you need LM and MN. The only two things we know in that proportion are LK and KN, essentially. So does that mean we just can't solve it?
No, of course it doesn't mean that. I know that that's what they're hoping at home to. No, it doesn't mean that. But what are we trying to find?
We're trying to find MN.
So I'm going to still just call this MN.
Okay.
Okay. How would I get to then to find out what LM would be? What would I have to do?
Okay, well, for example, like if let's say MN was 10, if I subtracted that from 15, I would get LM, which would be 5.
Right.
LM and MN make up that 15. If I want to kind of work backwards and find LM, I'm going to subtract MN from 15.
So I'm hearing 15 minus
MN.
MN, exactly. So just because they don't necessarily give you the parts, either part, doesn't mean that you can't solve it. It just means that you're going to have to compare them to that larger piece. Okay.
And guys, again, and we've said this before, if it helps, if you want to label MN X, then what would you label LN?
15 minus X.
And so it just depends on how comfortable, as long as you understand what you're finding and is that really the answer.
Okay. All right, so let's go ahead and substitute in the pieces that we know. So we now called LM our 15 minus MN.
Over MN is equal to 3 over 17. Now, I want to get in comments. The reason why Ms. Hograby kind of had us do this is because we had 2 unknowns in that first proportion that's in white there, okay? And then now in the yellow over there, we really essentially only have 1 unknown.
Right.
Okay, and that's the unknown that we're trying to find.
That's a good thing. We don't want lots of unknowns.
So she was relating that whole, they're giving you that whole segment LN to those pieces that we're trying to figure out.
Exactly.
Okay, so cross multiply.
So 3MN
equals 255 minus 17MN. And then if I add that, it's going to be 20MN.
Equals our 255
and then MN equals 12.75. Now,
if you said 12 and 3/4, that's the same thing.
What do you think about checking this? Would that be a good option?
I think that'd be a great option. So let's kind of break it down. This is saying 12.75 is the MN. What would that leave this to be?
That would be, what, 2.25? So if I actually put that in like that proportion idea,
right?
So 2.25 over 12.75, does that equal 3 to 17? And so we could cross multiply.
Sure.
Right? So 17 times 2.25 is 38.25. And let's hope we get the right when we multiply. 38.25 as well. So we know we did it right.
So that's just a check.
And guys,
it's a good check.
Here's the deal. I know that you feel comfortable with solving a portion, and that's good. But this is one chapter that a lot of people make mistakes because they set it up wrong. And then they don't check it. So checking the work is always a good option. Okay?
And and really even just checking to make sure, did I set the proportion up